Hi, this is Lab 5 for Physics 2211. I studied the net force a hurdle exerts on a runner when he collides with it and the conservation of kinetic energy. I wanted to look at the difference between a system consisting of just the hurdle and the hurdler versus a system with all the outside variables included in the system as well. Using a computational model, I will observe the change in velocity of the runner when the system is defined as just the hurdler and the hurdle. I will compare these results to the actual calculations when all of the outside variables are accounted for in the system. A what-if question that I made up just to spice things up is the energy principle satisfied in the system of just the hurdle and the hurdler? The results that I found are that the computational model, or the system of the hurdler versus the hurdler, the hurdle versus the hurdler with the net force of the hurdle that we calculated later, I'll show you that, calculated a final velocity of 3.95 meters per second versus the actual manual calculated final velocity of 3.5, which includes all the outside variables. As well, for the what if question answered, the energy principle is not satisfied, and I will also explain that later on. Newton's second law can be used to calculate an object's velocity, net force, mass, and a time step. In this lab, we will be using it to calculate the net force that the hurdle has on the hurdler, and we'll use that force that is calculated to implement Newton's second law into our coding to find the final velocity of the hurdle and hurdler system. The energy principle states that if no energy is leaving or entering the system, that delta E should be 0. We're going to use this in the end of the lab to check and see if the system of the hurdler and hurdle conserves kinetic energy. So in Tracker, I tracked my friend hurdling on the track. I did a video of him successfully clearing the hurdle. I'll show you that here. And I also tracked him over a hurdle where he came in contact with it. And that'll be shown here. I tracked the speed of the hurdler, and for the energy principle later, to see if the kinetic energy is conserved, I also tracked the velocity of the hurdle coming crashing down to compare that to the runner's kinetic energy. So the tracker graphs, you can obviously see a difference in the no collision position versus time graph, where the runner velocity is somewhat constant and actually increasing in acceleration. And then in the collision position versus time, you can see that the runner, and this is the impact point right here, little kaboom sign, you can see how he actually slows down. So I put in Newton's second law into my code, and this is the first time loop where we have the initial settings here. And then using Newton's second law, I found the net force from the tracker calculation. I just calculated that manually, and I inserted it into the second time loop, which is the contact point of the hurdler, and I put it here, as you can see. And then there's another loop that I'm not going to put in the video of the rest of the time that he's going over the hurdle. And this is gonna, I told the code to spit out the final velocity of, which is going to represent the final velocity of the hurdle and hurdler system. So after we ran the code, the computed results came out to a velocity of 3.95 meters per second, and as I stated earlier, the manual calculation of the final velocity was 3.5 meters per second. So we can see that there's a difference here. This difference is probably accredited to I didn't put in gravitational forces, a drag, or air resistance force, or any of the friction into the computational model. So here's the answer to the what if question. We see that delta E is equal to 0 in the system of the hurdle versus hurdler, and we have all of the initial and final kinetic energies calculated here, and those are plugged into this equation right here with the kinetic energy of the runner initial plus hurdle initial, and then the kinetic energy of the runner final versus the hurdle final. So we've just got 0 because the hurdle is at rest, and then after the calculations we see that there was more kinetic energy in the final part than the beginning part. So the final kinetic energy was greater than the initial kinetic energy, which disproves the energy principle for this system. Now, I think the reason that this is disproved is that for collegiate hurdles, they actually have weights in the supports that will increase once you kick the hurdle over to make it easier on the hurdler, and during the race, the weights actually exponentially increase the velocity of the hurdle going it down, making it easier for the hurdler to kick down the hurdle. So this was not accredited for, and so could have skewed the results. And you see that they're off by almost about 100 joules.